move to Rob then.
Rob, welcome. Thank you so much for your patience and for waiting. You are the last one, but thanks a lot again.
And we can see your screen, Rob.
But you are on mute, Rob.
That too.
No, you are on mute.
Sorry, yeah, it took me a while to find with all the different things open. You can hear me now?
Yep, we can hear you, Rob.
Yeah, that's good. Yeah, it took me a while just to, I'd forgotten to do that and I couldn't get, yeah. I've got whole screens of the PowerPoint and just a little bit of Zoom and I couldn't find the unmute button. Anyway, apologies for that. So anyway, thank you to Kate and Laurence for the kind invitation to say a few things here. So I thought I would, with this, you know, in my retirement, I can afford to be a bit more provocative with some of the things I say. And so where I've got to know Laurence is through an AI company, ostensibly, and mutual friends. But, you know, it's just looking at it now we hear so much about AI and machine learning. And actually what really matters is keeping it simple and just keeping it the fundamentals of physical properties. And I just want to give a few thoughts on that as we go through some things today. So, you know, what we need to look at is, you know, where are we in this so-called machine learning AI era? And in the end, you'll see it comes down to quality, and you know, and quality means physicochemical properties. So I've got just a little reprise about, you know, in a way, my journey through some of this. And, you know, just to follow on from the previous two talks, you know, we can see just how important HPLC methods are and how valuable those things are. And if there aren't people on the call who are converted to using HPLC rather than octanol water, for example, please listen. You know, I think it's a thing that we do need to get out there and get out there more. And then I think some of the other methods, you know, are incredibly valuable. You know, Clara's work and then what everyone's following on with. I think there's great potential in that. And measurements are always better than calculations. And, you know, we just need to understand what we need to know and do it better. So, you know, what are the important properties? You know, the simple things of lipophilicity, leading to solubility, and keeping it relatively simple. But of course, it then comes down to one of those things that always causes compromise in drug discovery, which is permeability and cell penetration. You know, they're perhaps related, but you know, let's just look at some of these things in context. And yeah, there's a few elephants in the room in this area as well, you know, in many ways, and we will come to that. And then towards the end, you know, you had a flavour from Paul yesterday about what I call the time and place for nature, and just thinking where we may go next with this field, and that's where we'll go. So I've got a couple of slides here I've reprised from an AI meeting I was at a couple of years ago, and this is the time when Exogenous had got the first AI designed drug to go into human clinical trials, and they were sort of trumpeting how they got there in just 350 compounds, which they say is a lot less than normal, and how this is record-breaking productivity, and how it would change the world. So, you know, yes, they did it in a nice way. You know, maybe over a beer like Paul and I do sometimes, you could discuss, you know, what's true there. But no doubt about it, there's a lot of money being given to these AI companies. There's a lot of potential there. You know, some of it is just making sure that the potential that's there is used in the most effective manner. Because there are things that I don't think are particularly helpful. And I also put this slide up at that same meeting 2 years ago, because this paper had just come out, and I think most medicinal chemists who saw this paper absolutely scoffed. You know, and my comment with this was, you know, either I'm missing something, or we really do have to think completely differently about antibiotics and how we do that. You know, this appeared in Cell, and you know, quite frankly, those things would kill almost anything. So the fact that the mice survived when they injected them, that I think they were rather lucky. And if you want to get some good perspective on this paper I read recently in Beilstein just, I think put this in its place and just said how completely promiscuous these compounds were. And it was talking about, how we need to think differently in antibiotics, but how we need to stay realistic within those things. I've just realized I need to put my laser pointer on it. It'll make life a little bit easier. But of course, any medicinal chemist is very familiar with these characters that were in in Nature a few years ago, all the work of Jonathan Bile and others, who identified particular structures and substructures that will always come up and produce nuisance results. And I suspect with some of these things, they've been involved with electron transport. We're not a million miles away from metronidazole. And, they're things that, a human brain could pick out rather quicker than a computer might be doing at the moment. So, these are some of the things that concern me about the field. And I'm sorry, this is just over publicity. I also looked at some of this, and I read quite an interesting paper because I kind of knew Stuart Russell a little at Oxford. We were in the same college a couple of years apart. And he's one of the leading lights now in AI. I think he's down out in California at Stanford, where he holds a chair. And he's doing a lot of writing and looking at things about what AI means and what the different kinds of AI are in a way. Looking back, this is kind of from the Nature summary about his book, and it looks back to the birth of so-called AI back at Dartmouth in the US in 1956. You've got some quite eminent people and Nobel laureates involved in a discussion, and some of them want to call it complex information processing, number crunching essentially on a big scale. And that's what some of the guys advocated that it being called. But some of the others decided to call a rather muddier thing and call it artificial intelligence. So that's almost the genesis of where this came from. So it's kind of coming back down to really what are we talking about in this? And most of the time in the context of drug discovery, it's going to be about complex information processing, making models, making good predictions. And, what really holds back the industry is data. Those of us who've been into big companies that have got lots of it know that some of it's curated better than other bits, but there is some stuff that can be done with it. But all of the startup companies would dearly love access to that data, and to make good models, you can't do it without good data. So these things do need a little bit of contextualization, and I think then Stuart goes on to talk about the boring yet beneficial tool AI, where you can do the things that computers can do better than humans and do more quickly and more reliable. And he puts that in kind of one basket, and then looks at the super intelligent AI. This is where you get into the realms of terminators and and machines that are in control. It may come into warfare, etc. That is quite different from what AI really is. And I think this may be available worldwide, but there's Stuart Russell gave the Reith lectures on the BBC last year, and there's some really interesting thoughts on there about where these things are going. So what is reality in drug discovery, and what's more balanced? My good friend Alan Jordan wrote a thing, just described what we've got at the moment as being the storm before the calm, because this is one of many things that medicinal chemists have been faced with many times over the years. It's almost reborn in a way. We've had previous times when we've been heard that predictive methods and computational things would take over drug discovery, but we're yet to see it. But it's just another tool that helped along the way. And one of the a decent comment, as often does came from Derek Lowe in the Pipeline blog, who was discussing AI, sort of saying that this isn't the end of a medicinal chemist, and it's not going to stop there being chemists, but it could be the time when there's an end of a medicinal chemist who doesn't look at it at all, who ignores everything that the computers may predict, and that can include the prediction of physical properties. And a sentiment I've heard in various places is not to consider this as being AI, but to consider it as being IA, which is intelligence augmentation. So a computer can never think yet in the way that a human might, and it won't have the experience. It can't see all the fuzzy bits around the edges. It just sees things in noughts and ones and makes decisions on those. There was a very good description in chemistry in Britain, which is the RSC's magazine, which says that yes, you can predict synthesis with computers, and it can do quite a good job, but it only understands rules. It doesn't understand some of the subtleties, like it may not understand the incompatibility of groups in a molecule. It may not understand protecting groups. So you need that kind of override from the human. And this kind of fits with what Exogenous should talk about, where they talk about their hybrid model, their central chemist, which is the combination of the computer and the chemist. So let's see that we can use this, and we can use it in harness. And I think one of the best papers I've read in the last few years was this one by Andreas Bender, who's just looking at what's realistic and what are illusions using AI in drug discovery. And I strongly advocate, if you haven't seen this paper, to have a read. And one of the key bits of it is that he comes out with various conclusions of what AI can do in terms of targets and everything else. But a key thing is related to the quality of compounds that go into clinical trials. And this graph here kind of illustrates his point, where in the early stages, where a lot of time is seemingly spent and people said, we must do this faster, it's not about doing this faster, it's about doing it well. Because the bottom line of this graph is the one thing that reduces time and reduces costs is the quality, and reducing failures due to the quality of the molecules. And you heard Paul speaking yesterday, he'll probably say more later. It's just the doubling of the success rate makes a huge difference to the industry, and that's just the difference between a 95% and a 90% failure rate, which is unfortunately where things are in the industry now. But if we put better molecules forward, then this big saving of things dropping out from not dropping out so often in phase 2 is what will make the difference in the end. So it's the thing about quality and how can you define that. Where you start could be important, and do we have this line of sight to quality? I haven't got much to hear, but there's a lot of thoughts you can have on where you start in a program. Although sometimes it may be a line of sight to where you end up, not where you start. But we could debate that for forever. But the other thing I think is very important is just confidence in the prioritization of compounds. What can we do in terms of properties to help pick the best starting points? And also in discovery is when do we know when we should stop? When do we know that we're not making the progress that we might do? So to illustrate quality, I just bring this slide back from my former employees that Paul was part of, where 10 or so years ago there was a big feeling that the GSK portfolio, as you'll see in the next slide, was not in a particularly good place. And one of the things that was done here was looking at the difference between the GSK portfolio in development and the top 100 oral drugs, and how could you differentiate them and how could you characterize them. And after a lot of effort and a lot of looking and analysis of the data, it was simply brought down to these three things that could be used to define the quality of those compounds. And it comes up from finally the dose. It's almost Paracelsus. It's the dose that makes the poison. So the lower the dose, the less risk you would have with the compound. And there's plenty of things to back this up in many studies. The compound being soluble is a huge thing. And it was agreed in the end that it should be facet solubility rather than just some other form of kinetic solubility. But nonetheless, a solubility parameter was very important in this differentiation. And then, as you'll see, my metric that myself and Alan brought together, and Alan Hill devised in 2009 when I had a broken arm, we looked at all the stuff about chromatographic data on log D, and you'll see a little bit more about this in due course. And the aromatic ring count, that is just simple prediction, was showing something about the developability and the chance of success in molecules. It was again another thing that independently differentiated the good things from the bad. And you get down to ideally you would have all three of these in the right place, and then as one or two starts going, you can see that more risk is coming. But if all three of it, you're in this very high risk space with a very little indication of previous success. And additionally, your dose solubility ratio is a really important part. And one of the things at the time we always used at GSK was to pick up a bottle that was a little bit smaller than this one, and it's saying this is the volume of your stomach. If you can't dissolve your dose in 500 mils, then you're in a poor place, because it's always going to be difficult to get predictable pharmacokinetics. So this is all discussed in drug discovery today, so I won't go into it in too much more detail. Beyond just a few things, it sort of shows where GSK's portfolio was and where the top 100 oral drugs were. So they just wanted to move somewhat in the direction to achieve more compounds with a higher chance of success and less, which are predicted to be very poor. It's not to say you won't find compounds that are red. There are some of these that are marketed, but it's just understanding the risk and having a balance in your portfolio. This down here talks to the DCS classification, which looks at the combination of permeability and the passive solubility in the context of dose. This is where this dose and solubility of 500 ml comes in. That ideally you want to be well soluble and well permeable to be in DCS1. You don't want to be soluble and poorly permeable, and you definitely don't want to be poorly soluble and poorly permeable. There are some things where solubility limitation comes in, that there are some drugs, but it's just it's a combination of these things to understand what success would be. So this is what quality looks like, and it comes fundamentally to the most important factors. And I always just like to say, like the politician, that the simple answer for the most important thing to control in drug discovery is lipophilicity, lipophilicity, and lipophilicity. So it's not like education, education, education. It is the fact that there are three types of lipophilicity that are important. We need to understand log D, which I believe is the most important one. We need to understand the partition coefficient, log P. And increasingly, as compounds get bigger and the chance for dynamic lipophilicity comes in, and you saw some things from Laurence yesterday, what we need to understand in that space of how we can better understand the behavior of many of the molecules that people are presenting with these days. In addition to that, we need to look a little bit at flatness, and we'll also come along with rotatable bonds. So together, all these fundamental things come together to help us understand the behavior of molecules. So I've talked about lipophilicity, and this is again a rather old slide now, but nonetheless it just shows the importance of Clara's work in particular, because this was just the analysis that Alan and I did of her data. And looking at this, it changed Alan from being a non-believer in chromatographic methods to becoming a firm believer. The fundamental thing across the top is, if you look at the solubility of your compounds, and these are the values that are typically used at GSK to describe poorly soluble, intermediate, and reasonably soluble compounds. And as you see, there's not a huge range between good, the bad, and the ugly, and this does kind of fit in with predictions from the general solubility equation, whereby if your log P is 3, that you could get any of these. So if you get any higher in log P, your risk in becoming a grease ball and not being very soluble. And if you look at the European Pharmacopoeia, you will see that at this point here you're being described as practically insoluble. So they're not pulled out of thin air, these things. But what you can see, that if you look at the measured optimal water log D against ACD predictions, you can see that insoluble compounds, there's almost no correlation between the prediction and the measurement. And this here is the line of unity. As compounds get more soluble, you can see the correlation gets better. And this to me was revelationary. You can see a box plot that shows the behavior. This one down here is a heat map that Alan produced, just to show you that if you had the chromatographic measurements of lipophilicity, you had this nice normal distribution of values. And yes, GSK was making lots of compounds up here. I fear there might still be a few, but I think things did change before I left. If you look at the same compounds with measured optimal water log D, you do not see this normal distribution. And this is due to this tailing, or almost a random number generator, because the compounds are too insoluble to give you reliable partition between the phases. But ultimately, you get to a predictor and down here and the measurement from chrome log D, and you can see here that amongst very many compounds, there is a very strong correlation. And importantly, on the right-hand panel, this is irrespective of the solubility of the compound. So even for the compounds that are poorly soluble, there is still a very strong correlation, and each of these graphs have got a line of best fit and a line of unity within them, which is showing the value of the method. And then when I had time to look at these in detail, it did show just how important these numbers were and how much better they were for drug discovery than using the flawed measurements that the optional water brings. And there's nice work that I know Laurence I've seen speaking about, and Mike Schultz did the same. But they just show you that you just simply haven't got the sensitivity in the measurements to detect things at the right level to understand what was going on. And and it's compounded by the fact that they're not perfectly immiscible and hydrogen bonding and so on and so forth. So there are many reasons why octanol, it perhaps served the test of time for a while, but I think in modern discovery, it has certainly been superseded by these methods. The next slide is just talking to a little bit. So when Clara first introduced this to us, I guess from experience, she picked a line that was trying to mimic the octanol water scale. And it was always known in those days as chi log D, based on the chi value, which is related to the percentage of acetonitrile to get the compound off. And then again, but this is calibrated within a set of standards that Clara would tell you all about. But in practice, with extra generation of data, it was found that there was this crossover. So when you got to more hydrophilic compounds, you were getting a higher value than you would expected, and the value was rather lower for more lipophilic compounds. So there was just the idea that could be correct for that, and a new equation was developed which changed from being chi log D to chrome log D, and this is where the parallel lines came in. I think, Clara, it was Alan who just made the mistake. He picked the number and saw that the correlation was there, saw they were parallel. But then when he saw this, rather than changing the constant here, the decision was made to keep this number in. So you were getting this slightly higher figure just to make sure there was no confusion between the octanol scale and the chromatographic scale of the same thing. So this is discussed in some of these more recent papers. And just to remind you that this parallel, this parallel universe, so you can see how it's parallel in this plot here. But it's just very important that what is there is reproducible, it's reliable, and it changes things. So when we're in optimization, what we have to do in drug discovery is we need to get all of these things in terms of potency, safety, absorption, stability, etc., etc. And what does lipophilicity influence these? I'm sure most people know that very often if you make a compound less lipophilic, you lose your potency. And this speaks to Mike Hand's paper where he talks about molecular obesity and other obsessions in drug discovery. So we just tend to make things lipophilic because it makes them more active. But we know that if we reduce lipophilicity, these things are enhanced. But the issue will come with absorption. And just to move on, this is a diagram that I've been reproduced many times. It's in this review I wrote in a book edited by Nick Meanwell, where you just look at various developability assays. If I just move it over, it says what they are in more detail. So it's the CYPs, it's protein binding, it's solubility, permeation, etc., etc. And we can also see where we come to hERG and indeed promiscuity, which is rather more driven by log P than log D, but read the paper and there's more detail there. And this is simply coloured by the percentage of compounds that meet a certain standard in these assays, a standard that is indicative of risk. And so it's all coming back to this idea. We are using PFI here, so we're looking at the impact of aromatic rings over and above lipophilicity, and with some of these, you can do it on lipophilicity alone, but more often than not, if you add the aromaticity into the equation, you will see a better striation of a better differentiation between the outcomes. So, look at the papers for more details, but you will see that these things are reasonable predictors. And, I had this thing that appeared in January that made me feel really good when Pat Walters published this blog, And I don't think Pat's on the call, but Pat is one of the gurus of most people doing things in the computational methods, and his practical chemoinformatics is a very well respected and very well read blog. So for him to be saying that the solubility, the venerable solubility forecast index was still outperforming any deep learning or AI model, I think sort of says something about the robustness, despite the simplicity of the model. I'll never say that you will predict an exact solubility for this, but it will tell you what your chances are of achieving good solubility or not. And then when we realized it was important on so many other things, that's when it changed from the solubility forecast index to the property forecast index. So, it's keeping it simple, but it's a very valuable and very useful measure. But what you find when you look in more detail, we start looking at the ADME constraints that get worse as it gets a bit more lipophilic, and we get this tipping point round about 6, 7, which is a low, with 2 aromatic rings on average in drugs. Then this is where we're at that point where lipophilicity is around about 5, and we will come back to that number in a second. We're also starting to get more off-target risks. So what we need to be doing here is we need to be optimizing lipophilicity and aromaticity in our compounds. You heard about Paul yesterday saying that aromatic rings don't change. So the main thing that we're optimizing here will be the lipophilicity of the compounds. So we're not improving the lipophilicity, because if we improve our lipophilicity, that would suggest that you make the compound more water soluble and you move to the left of this graph. But if you do that, you lose your permeation. So that's why it's probably best now to talk about optimizing lipophilicity, not improving it. And Paul brought this paper up from Merck during discussions yesterday, where Merck is still railing a little bit against these things, but most of the things they've said in this paper and the trends that they suggest and how you can balance all of these in your molecule, I agree with most of them, although, as you will see, I disagree that lipophilicity increases permeability, because you've seen in the previous ones that there is this bell-shaped curve that's involved with this. So, that's another paper to read, a slightly different view on it, but, let's look at what the impacts are. Of course, where you get very high in lipophilicity, very few drugs are found there, and also we've got all of these risks. So I think, enough people have got the messages about where not to go in drug discovery. There was also this book that I was part of, so I wrote a chapter about solubility in this book, very nicely edited by Patrick Schneider, who formerly of Roche. And he wrote a really nice chapter to start it off, where he looked at the different things, the different ADME challenges that there are, and he looked at the impact of different changes and what they would do to the outcome in these particular assays or phenomena. And you will see that by and large all the chapters will be telling, or almost invariably all of the chapters will be telling us what the impact of lipophilicity would be. So I can thoroughly recommend this book. It's a very good resource for many things, but again, keeping it simple, looking at lipophilicity, it will impact most of the challenges in ADME. And ADME is the biggest thing we have to do in discovery. But the elephant in the room now is, what about permeation? And I'm sure people have seen this long-running debate between Doug Kell and the group that's probably centered around Lee Dye at Pfizer and one or two others, where they're almost at loggerhead with each other. But in a way, I think the compromise is that somewhere between the two extremes is the answer. I think these guys will certainly concede that there are some compounds that go through membranes on a protein. You go back to Lipinski even in 97, and he tells you that some compounds are transported, and they're almost exceptions to his rule. But if you listen to Doug Kell and people who work with him, he will suggest that all compounds will actually go through the membrane on a protein. And we will look at some of this in detail in the next slide. There's lots of papers in this long-running saga to read. There was an interesting debate last year that Nick Meanwell organised over 2 meetings through the ACS, where Doug Kell spoke, and I thought spoke very eloquently. And what I didn't like about Lee when she spoke, all she could give as an answer to permeation was, it doesn't obey the rule of 5. And I'm afraid, as I'll show you, the rule of 5 isn't very good on permeation. So this is the crux of Doug's argument, where he says if you actually look at the membrane, it's replete with proteins. There actually isn't that much exposed bilayer for a compound to go through, even if it did, in his view. So it makes more sense to be there, for there to be this mediation by these proteins, many of which will probably be hydrophobic. So, you know, that's his tale. But in a way, it doesn't really matter, because what we're talking about is a very hydrophilic compound would diffuse very slowly into a lipophilic environment, notwithstanding what it might need to go through the polar head group. So if we're down here, and this is from one of the reviews looking at an old set of drugs, I think this graph comes from the 1980s, where people have measured compounds, so they are drugs, so they're quite likely to be soluble, so we can probably believe these oxygenol water figures, and we can see this nice bilinear response to lipophilicity in terms of the transfer of the flux of compounds in permeation. So when we're down here, K1 is rather slow because we first be in the water. When we get over here, when we're very lipophilic, you want to get out of the water, but you want to probably stick to that protein. So K2, to get through to the other side, is rather slow. And this is the basis of that bilinearity. And without an active process, this is going to be the same, irrespective of which mechanism is done. This comes from our review. When I looked at Pampa data, the similar thing comes if you look at CACO with inhibitors of efflux. You can see that the basis of a bilinear response, because we're looking at high permeability, intermediate, and low permeability in the Pampa asset GSK. The grey bars are reflective of those where the experiment had problems because there was a poor recovery of what came out. And you can also see a reason from this in a paper that I recently discovered of Scott Loki and his team, where he looked at a series of cyclic peptides and looking at their so-called passive membrane permeability, the measured values against A log P. And again, you can see this very familiar bilinear pattern. And what's really interesting, when you get to this side, you can see that the recovery of the compound is relatively poor. So it's probably suggestive of things actually sticking a bit more in the membrane. What is quite interesting, though, is the indication of size. We talked a bit about size yesterday. So there probably is an upper limit of how big you can be to get through by some, membrane burrowing method without, we did talk about phagocytosis and maybe other things that could happen when you get very big. But you can actually sort of see when you get down here, these are probably some of the more hefty compounds that are causing this lesser permeability. But again, this is about rate, not about equilibrium. There's probably another discussion to be had there. So, we can see that there is this bilinearity to it. So I want to very quickly go through this story that I probably have told before, and people may be familiar from some of the publications, of the work that Alan Hill did back in, it was 1989 this started, where in the days of old-fashioned chemistry, where you took 5-HT, the natural ligand for a receptor, and you made analogues of it to modulate the pharmacology. So these are the old 5-HT1D agonists for treating migraines, sumatriptan from Glaxo, and then welcome compound was zolmitriptan. So you can understand the classical medicinal chemistry going on here. And Alan wanted to understand the poor behavior. There's Alan with a picture he really likes of himself. He looked at the lipophilicity of these compounds, and this is where he used calculated molar refraction, which is a physical property of a compound, depending on it. The bigger it is, the more it refracts it, essentially. And this does correlate with weight, with size. And it was just a measure he used to try and confuse the chemists, was what we'd often say. But this is a thing that stood the test of time as the best way of differentiating things. And the original model he proposed was that if you were small and hydrophilic, you could get through via the paracellular route. And this was well known about the little gaps between the cells in the brush borders. And it's an old-fashioned strategy for making drugs. As you get a bit more lipophilic, you're in that position where you could probably you get in either way if you're soluble enough, or you could perhaps start going in via this transcellular route, via the double partitioning process. So this was the model that he produced. I guess in 1989 there weren't quite as many drugs available, or certainly not ones that he had measures on. So he could sort of see where things would be. But clearly, if you were hydrophilic and large, it was likely to be poor because there weren't very many drugs in this place. And this is one of the original graphics from the age. You can guess where many of the welcome compounds were. They had quite big tails coming off of this particular ring. And Alan said to Alan Robertson, who was leading the program, you actually need to make your compounds a lot smaller to get back to this space to get decent availability. And to cut a long story short, you've got log D CMR on the base of this 3D graph. And you can see that indeed, when you are smaller and staying hydrophilic, you're getting a better plasma concentration after oral exposure. And this was 311C90, 1990 was the year it was made, and zolmitriptan. And this is what set on the path towards understanding permeation. So when we moved to Glaxo Wellcome, when more data came in, and I guess Nan Hersey and Chris Luscombe did a lot of work around this, just understanding how you could differentiate good from bad. And this is oral bioavailability here, not just permeation. And these were based on rat data, and Chris called this linear discriminant function line that would just discriminate between good and bad, and the theory being, judging by the distance from this line, will be the likelihood of getting good permeability. And this has really stood the test of time, and you'll see this evolving through the years when we've gone from a calculated log D to measured, and then the GSK Chrome log D, and ultimately calculated Chrome log D. You know, this is making the model tighter, and the errors are getting less. Of course, I always like to point out that I'm fully responsible for the compounds down here that are way away from everything else. So this is my days on working on the INOS project. So it is nice to break rules at times. So, you know, very much about this is quite compelling in terms of the compound classes. This is from the supplementary data of one of my recent publications with Chris Timwith, where it shows you, you know, green means these things have got good bioavailability, red means they have poor. And if you look at, I know this is comparing, you know, yes and no, but there's a very strong separation, you know, either side of this line. You know, most of the greens are this side, most of the reds are this are below. And then the parallel lines are almost a bit where the model isn't so certain. I guess there's a statistical distribution in there. But those lines have got tighter over the years as the chromatographic data have come in and the predictions have got better. And you can just see via the distribution just how much it does sort the wheat from the chaff in all of this. But we have talked about the odd outlier. And we looked at this in some detail in the paper with Chris. And when you start looking at the compounds that are breaking the rules, and these are some of the ones that are starting to appear outside what you might call rule of five space, there's a bit of a pattern in that many of these things are natural products. I've actually covered over what the color code is. It's all in the paper. But this is where we're seeing the beta-lactams, the carbohydrates, the amino acids, the nucleosides. These are things that are natural products or natural-looking substrates. We do have this region here, of course, where we've got small hydrophilic molecules that would be paracellular. But if you do a squint, you can actually see that the meat of the distribution is in this area where we're seeing the best chance for good permeability. So, you know, there is something about just using the simple Chrome log D and this size that is standing the test of time in understanding permeation. And it was seeing this that really brought home to me about what the AbbVie MPS told us. And when I saw the full storybook when Phil presented it, it really showed things that were backing up with what we were seeing. And I kicked myself for not understanding this absolute value of log D -3 and the mathematical implications of that. So if you look through the Pfizer paper referred to here, you will see just in their bin pamper data, they would see that, you know, the maximum permeation was being found at C log D of 3, which is equivalent to 5 on the chromatographic scale, as we discussed earlier. And one of the things that goes into the AbbVie score is how far you are away from 3. So if you have a C log D of 3, you score 0. And the higher your AbbVie MPS, the lower that number is. And don't forget, this was developed on their behemoths, on their very large molecules, what they call EROF and BROF, so 5 to 700 and above 700. And this was done from empirical data by just putting, as Phil said, getting the compounds in the critters. They could get some real data, and they were observing oral bioavailability. And they then looked at what would come to rationalize it. And it came down to this optimum log D, which is consistent with what we were seeing. And then also the number of aromatic rings and the number of rotatable bonds in the structure. So you minimize all, you keep this close to 3, you minimize either or both of these, and you will get a compound that's likely to be more orally bioavailable. So Chris and I looked at this in terms of less than 500 weight, then 5 to 700 and 700 and above, and you can still see in terms of the AbbVie MPS scores, okay, they're a bit lower when you come to smaller molecules, perhaps not surprisingly, but you can see that these numbers do differentiate between the apparent permeability rate in the Pamper assay. I'm hoping this is a genuine thing about permeability rate and is not just a lipophilicity surrogate, but that is perhaps a discussion for the panel later. So we're seeing what AbbVie are reporting. We've recapitulated this in these data, and a lot of these things here are on a lot of measurements, and we can see that this log D minus 3 is a key part of all of this. So I put these slides in just whilst I'm sort of saying one or two things that are wrong with the rule of 5 and why it's time to put it to bed, as we discussed last night. I put this one together. So this is from the supplementary data of the paper with Chris. If you look at just a random sample of GSK compounds and you look at the calculated log P, you can do it. It's not quite as clear from the measured data, because I just don't think there were enough data to show it in this way. But you can see against bin molecular weight that there is this steady rise in the average log P, and the fact that these dots, if you're familiar with box plots, do not overlap, it's showing you that there's a statistically significant difference between each and every one of these things, and this is at an alpha level of 0.05. I think you can still get them apart at 0.01, but it's just showing you that trend is there. But if you look at drugs, and this is the set of drugs in Mike Schultz's paper that I was sort of critiquing a little in here, as well as just looking at it in the context of the rule of 5, you can see this Darwinian process that if you look at drugs, even when you get to high molecular weights, you can see through the statistics here there are none. There is no separation when you get much above 350 molecular weight. The average lipophilicity is in that very narrow range that you were seeing in Paul's presentations yesterday. So in a way, this is nature influencing, or selecting from everything that's made. And I put this in as well. The point was made about hydrogen bond acceptors. Again, this is looking at log P against molecular weight, just a plot of them. The fact that there is a semblance of a correlation, but again, I'm not claiming anything there. But what really brings it home there is you can just see, as the colours change, that is just simply in terms of the number of donors, the number of acceptors, hydrogen bond acceptors in that molecule. And you can just see that, the smaller you are, you can see that, we're generally 0 to 4 is blue, 5 to 9 is green, 10 to 14 red, and then when you get very big, it's 15 to 21. So this is exactly what Paul was speaking to yesterday. And finally, while we're doing it, just to repeat some graphs that I've shown a few times over the years. This is the original one from 2010. This is the one from 2020, which shows that if you look at PFI bins along the bottom level and you look at molecular weight bins on the y-axis, and then the green and the red is the distribution of solubility using the values that we saw earlier. And you can see that if you've got within a molecular weight range, you can see that solubility gets worse as PFI gets higher. But if PFI is constant, you can see that the distribution barely changes. And it's the same in 2010, and it hasn't changed hardly at all in 2020 on a different set of compounds. So there are box plot statistics in the supplementary as well to address some of the detractors. But to me, this is a very clear message that molecular weight has absolutely no impact on lipophilicity. It may have some correlation with CMR, so size perhaps matters in terms of permeation, but lipophilicity is probably more important as well there. So these are some of the numbers that are suggesting it's time to move on from the rule of 5. So finally, Paul was hinting a little bit at this last night, and one of the things, being semi-retired, I do have a little time, and there are plenty of places not far from where I live in the middle of the countryside in the UK where I can go to view nature. And I'm very fond of photographing butterflies, and that got me talking to my old friend Nick Turner, where we were swapping photos, and we were trying to get all the butterflies photographed on the British list. So I've got some time, and there's a place for some nature. And through various discussions that we were having, we were looking at some of the work of Herbert Waldman and Ron Quinn, who's an old natural products chemist, and then Paul came in with some of his data and some of the analysis that you saw yesterday. And it was just kind of exploring the concepts of what nature can teach us in drug discovery. And is there a logical case from some of the things that we found in here, and you saw a flavour of where Paul is taking it next, that Paul, I think I used 10 to the 60, I've seen 10 to the 70 in papers about these potential number of drugs. And if you look at some of the analysis, there are actually quite few rings used in nature. And we saw from the preview last night that some of these natural rings, and just putting them back together in this pseudo way that Herbert talks about, that there's perhaps rather less compounds to be made than we might think. And surely we could use intelligence augmentation or artificial intelligence to recapitulate compounds with more natural motifs in our molecules. So what the logic would be is that if your compound ultimately is made by a protein, and Nick and Sabina are experts in enzyme catalyzed chemistry, if your compound has already been recognized by an enzyme, it should then be recognized by another protein, which might be your transporter and or your target. So there's just a logic that nature's been evolving to do this, and Ron talks about the fact that this notion in a way is validated by natural products. And we're talking about truly organic molecules here, perhaps not petrochemicals, which is, to pardon the pun, it could be an inflammatory statement. So, are we using what is known as natural intelligence rather than artificial intelligence? And there's some wonderful books I've been reading since the effect about natural intelligence. So, do we pay now to make better molecules rather than just the petrochemicals? Or do we pay later in lesser success? So there's a thing to think about. And this kind of does fit with some of, going back to Doug Kell's hypotheses. He talks about the fact that he believes that the transporters evolved to bring in beneficial molecules from our diet, from our food and our nourishment. And if you can get those things inside the cell where they can have an effect, it's beneficial. So that the transporter would have evolved to select for these things rather than kick them back out again. He's even got this rule of 0.5 rather than 5. Talks about the metabolite lightness of most approved drugs. And furthermore, he's proposed this set of compounds, which he said will explore space. So these are the purple compounds overlaid on my favorite log-D CMR plot. And you can see that, that what he's proposed is very similar, based on the analysis that he did, to where we're seeing natural products or drugs lying based on this particular analysis. So, are there patterns that are important? So, just towards my penultimate slide now, I think we just need to revisit absorption. We know that up here, and you can call this the Han-Kesru sweet spot. You'll see me talk about this in some of the papers where the reference is there, where you may get this generic absorption or particular transporters that are not quite so specific. And and this is where the LDF line and the statistics are very strongly in favour of compounds being absorbed. And actually, if you look at many of these compounds, there's a lot of black spots up here. These are the compounds that Paul calculated through Natural Product Scout to have quite a low natural product likeness. But if you look below the line, you can probably see through this that there are many green spots, and these are the ones that are very natural product like. And this is where many things exist that are likely to be transported. We know we have a region here for paracellular transport, and maybe there's a region over here where the ABV principles come in for beyond the rule of 5 compounds. So I think that understanding absorption, it just isn't as simple as lipophilicity. I think we might need to treat some of these things in rather different ways based on the makeup of the molecules. You know, can we predict which transporter they go on? You know, is this generally more generic? You know, it could be through the membrane, or it could just be some rather non-specific interactions with proteins. But I think it's an area that's quite rich. But working with my friend Liz Fulham we were talking about things getting into TB, and this is my final slide, but looking from the Time and Place for Nature paper, where if you actually look at antibiotics, so these are sub-classified originally from the Fulham paper, where all the circles on this diagram, and this is the LDF line from log D CMR, so down here is predicted to have poor oral absorption. You can see that the majority of them are below the line, and the size of these things is talking about the natural product class probability. So most of these antibiotics that are below the line are akin to natural molecules. And even some of the ones here that got lower scores, there's some of the sort of semi-synthetic beta-lactams, which the way the Scout program works, it tends to mark them down a bit. But you know, to me, that's quite a marked differentiation in a class of drugs. So perhaps it's not a surprise that, you know, using what we've done for the last 20, 25 years in drug discovery and high throughput screening against targets, perhaps that's why there haven't been so many antibiotics discovered. And you know, there are many papers by Dean Brown and others that, you know, that bemoan this lack of success in the area. So maybe we really do need to go back to nature to discover more antibiotics. So hopefully I'm not too far over time. You know, you've seen my provocative title. And hopefully going through this, I've given you a snapshot of the various sort of thoughts and views on some of these things. So we know that quality is what matters in this era. You know, a huge advocacy from me, and you know, and a great deal of gratitude and admiration for Clara's pioneering work and others as we're now hearing. You know, really switched me on to the possibilities there. You know, what is important, you know, just keep it simple if you can. It does seem to work. And it's what we're all about, I guess, in this forum. And just understanding permeability and cell penetration, you know, the importance of log D, and perhaps why the rule of 5 has had its day. And, you know, is there this time and a place for nature? So that is a bit of a provocative thought, and we'll see where it takes us next. So finally, I should thank the many people here. Yeah, sorry, it was the survey came up and stopped my mouse working. Just so you know, so I've name checked many people as I've been going through here. People who I've worked with over the years, mostly at GSK, some outside. You know, some good conversations with Doug.
Like big pressures you can put.
Yeah, I need to fill the slide anyway.
So someone's unmuted. And then, so thanks to all of those, and of course again to Lawrence and Kate and Annalisa and Peak Analytics for putting this together. So thank you, and thanks for your attention. And there's me and butterflies, and you can see the derivation of my company name there.
Thank you so much, Rob. A lot of